So tonight what we want to talk about is function notation. This unit is really a lot about notation. We talked about interval notation today in class, and so we're not learning new concepts, but we are learning new ways to represent those concepts. So these have all been things that you've been doing in math for a while, but now you need, we're learning the formal way to write it. And so today we want to talk about function notation. Function notation is a way that we represent functions. We talked about functions. One input has one output. Every input has only one output. And we talked about that. It's ways of representing a relation. All functions are relations. And one of the ways that we mentioned that you could represent a relation or a function was an equation. And so function notation is something that we use a lot with equations. When you guys have done equations thus far in school, you've gotten very used to things like y equals mx plus b. We've kind of got into this habit of there's an x and there's a y, and that's the input and the output, the domain and the range, and this is the notation that we're used to. When we use function notation, instead of y, it's really the y that is getting like a new way to write it. This doesn't really get messed with. The equation and the expression that it's equal to, that's really represented the exact same way. What we're messing with here is the y. With function notation, instead of y, you will see something like f of x. Okay, these two things are the exact same thing. They're just different ways of representing the exact same thing. We have an input, the x. It's going to be equal to the output, whatever comes out of it, y, or in this case, we now have f of x. So let's talk for a minute. The way we say that is f of x. It is not f times x. One of the things that you want to kind of get used to here is that the f is the name of the function. We're giving the function a name. This helps us to reuse it later very easily. I go back to the mathematicians are lazy. We don't want to write anything that we don't have to. And what function notation allows us to do is it makes it much easier to say that we want to plug things into the function because we're giving the function a name. You will see different letters there. Sometimes we will have g of x. That's just a different function. That would indicate that these were two different equations, two different functions. You'll see h a lot, h of x, those kinds of things. So it can be any letter. It can be a lowercase letter or a capital letter. It's just a name. This is the name of the function. And this together represents the output. It's basically your y. Now, the reason we like to use function notation is that we can compact things together because this whole thing represents the output, but what's in here is a way to represent the input. It's saying the function of x, meaning that x is what I'm plugging into the function. That's the input. And so what that allows me to do later, for example, if I have that f of x is equal to 3x plus 2, if I want to plug something into this function, all I have to do is say f of 2 equals question mark, blank, something along those lines. Because what this tells me is I want to know what the output, f of 2, is equal to when I plug in the input 2. So that is what I want to plug in to the equation. So this tells me to take 2 and plug it into this expression. And so that means that I'm going to do 3x plus 2. Kind of think of the x as it's the empty slot. It's where we're plugging things in. It's where the input is going to go. So I've got this blank spot where the input is going to go. That's the input that I want to put in there. So I want to plug in 2. So that's going to be 3 times 2, which is 6, plus 2, which is 8. So f of 2 is equal to 8. I plugged in 2, input. I got out 8, output. Input, output. I'm going to say input and output a lot. The way this boils down is you will start to see, instead of having like an XY table, sometimes on papers you may see that we have an X, f of x table. Because again, this is the input, this is the output. What is it going to be? So when we plugged in 2, we got 8. And so that is our input and output. Again, if we have a mapping, if we're using function notation, we have our domain and we have our range. And so our mapping could have, instead of x and y, it would have x and f of x, and you could still have a mapping. So in this case, it would be 2 goes to 8. So this is just a different notation for y, is what that really boils down to. If we look at some example problems, for example, if I have f of s is equal to 8s plus 15. So s is the input, so this is where I'm going to plug numbers in. And so then they can ask me all of these questions without having to rewrite the equation over and over and over again. So if I want to find f of 7, that means I need to take 8 times 7 plus 15 and figure out what that is equal to. So if I do 8 times 7 plus 15, I get 71. So f of 7 is equal to 71. It doesn't matter what kind of number you're plugging in. You can plug in 0, you can plug in 2.5. Those are all things that we're going to plug in. So this would be 8 times 2.5 plus 15. That's the equation. This is telling me to plug that into that equation. So 8 times 2.5 plus 15, and we get 35. So f of 2.5 is 35. If we look at some other uses, sometimes we have a table. Okay, so we still want to think about input and output. If I have a table, this is, we're talking about age. Okay, so that's like a time. How old is the person? That's our input. This is our height, or the child's height, so that could maybe be h of t. Okay, so this is my input still. This is how tables work. First column input, second column output. So if this is my h of t function, or my h function, when this says find h of 7, it's telling me what the input is. So I don't have an equation to plug it into, but I do have a table to plug it into. So for an input of 7, I look for, okay, here's the input of 7. What's the output for 7? 49. So h of 7 is equal to 49. Input, output. We said yesterday there are 5 ways to represent relations and functions. They all are talking about points. So they have an x and a y. There is an input and there is an output. So whether they give it to me as a table, if they give it to me as an equation, if they give it to me as set notation, this number in here is always going to be the input. And then what I am looking for, this whole thing is supposed to be equal to, is the output. Plug a number in, get a number out. Plug a number in, get a number out. You can work backwards from that. If you look at this, this says, okay, h of a is equal to 61. So what is a equal to? So in this case, they gave us the output, and we are looking for the input. So that just means vocabulary-wise, again, it kind of gets down to a notation vocabulary thing. They don't have to have a lot of words here. If they give me this, then I know that the output is 61. So I look and find, oh, where's the output 61? Here's where the output is 61. What was the input that gave me an output of 61? Oh, that would have been 13 years. So when they're 13 years, we would have an output of 61. So we have our age and we have our height, and so they're giving us this notation represents the output. That is the output. We're looking for the input. This works in one of the other ways. What if they gave us a graph? Because we said a graph is just a set of points. It's a relation. So again, this is my time, and this is my distance. And so this is d of t. All right, this graph is representing d of t, the function d of t. So if they're asking me to find d of 2, this is the input. Input is the x value. I'm looking for the output. Output is the y value. So I want to look, where is x equal to 2? So here's 2. Well, where does that actually cross the graph? That's at that point. That is where x is equal to 2. Well, where x is equal to 2, that is the point 2, 4. So where x was equal to 2, the output, the y value that goes with that x, is 4. If I want to find d of 5, again, this is the x. I'm looking for the y. So I find, okay, here's 5. So where was x equal to 5? That's this point. So this is the point 5, 11. So if the input was 5, the output was 11. Works both ways. Down here, that's the t. They're giving me the y. I'm looking for the x. I don't know the x, so they've given me the y. So if I want to know where y is equal to 2, then I'm going to have to go to y and figure out, okay, so here's the point. This is the point 1, 2. So where y was equal to 2, I got an x that was equal to t was equal to 1. But I have to be careful, because also look over here. Here's 2, but this point over here is also 2. This is like 9.5, 2. Okay, 9.5, 2 is that point. And so when I look, sometimes if you're working backwards, there may actually be more than one point that that could be equal to that. And so you want to make sure that you're very careful when you're working backwards, because we said x's can't repeat for it to be a function, but the y's can. So if they're giving us this y value, there were 2 places in this particular function where the y was equal to 2. So we did have to give both of them. But the idea here with notation-wise is the number inside the parentheses is the input, the x. What it's equal to is the output. So whether they give it to us as a graph, or whether they give it to us as a table, or whether they give it to us as an equation, we have a number to plug in and a number that we get out. And so we can solve and we can plug things in and we can evaluate these expressions using function notation.